Well, welcome back to our course on system engineering. We are working through the beginning sections of this introduction, overview, and basic knowledge, leveraging the best of a handful of different textbooks. And so we gave an introduction to the course. We then talked about, from a high-level sense, an introduction to system engineering. Now we're going to get more specific into an overview of the systems engineering design process. And we'll be reflecting about this more in future chapters, but let's continue to do this introductory layer as we pass through this material. So in this chapter, it provides an overview of the details that come to by presenting a number of basic concepts. And so these include the operational concept, the objectives, requirements, functions, items, components, interface verification, validation, and acceptance. So we're going to get a chance to see the various elements within the full life cycle. And then we're going to see the relationship among these concepts in this chapter as well. So some key terms to be thinking about. And so systems engineering, so the first thing you need to have is a system. And so what is a system? So it's a set of components that can be consisting of subsystems and segments acting together to achieve a set of common objectives via the accomplishment of a set of tasks. A system task or function, this is a set of functions that must be performed to achieve a specific objective. And then for human design systems, this is specifically defined a set of segments, that is hardware, software, physical entities, human and facilities acting as plans. And so you have these entities that are related to one another, and they all have to be in concert in the way that they're supposed to flow. There's interfaces, so which are designed to connect the components. And so you have these points of demarcation and information that's defined of what actually flows between them. Maybe you've heard the term API. So from a software sense, maybe that would be something that a few of you may have some familiar with. And so to achieve a common mission or fundamental objectives, that's what it's meant to do. So it's supposed to fulfill a set of specifically defined objectives, and is subject to a set of constraints. And finally, through the accomplishment of a predetermined set of functions. So those are maybe some terminologies that maybe you haven't heard that might be useful for you to be thinking about. And so here we think of the context in which a system is at. So you have system, this is where what we're designing, but it has to be existing within an external context. And so things need to be flowing in, things are flowed out, but there's also some things that are a little bit higher, more removed, that can impact this, that can cause some concern or needs to be aware of into the larger context, something that might impact an external system, which then again would impact the system. So maybe just keep that in mind in terms of that. So we have a couple of tables here from Booty. And so the first is the functions of the design process. And so this is a lot of detailed information. And so I won't have the time to go through this line by line or box by box. But let's just think of the design functions. And so first we needed to be defining the problem to be solved. We need to develop and evaluate the alternatives, define the system level design problems being solved. So here we have sort of the formulation process. Then we have the developed system functional architecture, the physical architecture, and then the allocated architecture. And so this is where we get into the specific ways of how we plan to be making this capability operate. Then we have to be figuring out the interfaces and then the qualification for each of those. And so for each of these things, we have the inputs and outputs that must take place. And hopefully as a result of this course, you'll get some more perspective on that. So the first thing we looked at is the design process. Now we have the system level design problem. And so here, the operational concept, define the boundaries and the external system diagrams. So top level context, develop the system operational objective hierarchy. You want to be developing, analyzing, and refining the requirements. You want to ensure the feasibility and define the system requirements and obtain approval. So this is more of this is the design. So we're not doing the full life cycle, we're just doing the design. So we have the overall complete life cycle design. Now we have just the system level design that we talked about with this chart. And then we have the other end where now we're talking about the integration and test. And so doing early validation is important. Remember this, as soon as you can find an issue, the better, because it's going to be cheaper to do it then than just waiting a little bit longer. So early validation where possible, you want to be doing the integration and verification testing. At a higher level, doing the system validation testing. And finally, the acceptance testing is where you're working with your stakeholders and customers. And in a similar fashion, we have the major inputs and outputs for each one of those. Key concepts, an operational concept. This is the vision, the mission requirements and scenarios. This is like, you can think of a day in the life of the system. How is it actually going to be operating? The external systems diagram, this is where you think about the various inputs and outputs that the system has to be passing back and forth. So the terms that Booty uses here is a meta system. And for the objective hierarchy, this is the cost, schedule, and performance measures of effectiveness. So that's what you're going to be building to as you're doing the system design and manufacturing. Finally, having the requirements, and there's various types of requirements, input and outputs, technology and system-wide requirements. You can have trade-offs and system requalifications. All of these are involved in the requirements development and validation process. So we have some more key concepts. A function, this is a transformation by system of inputs into outputs. So you can be thinking of a function as a black box, and sometimes that can be effective. And I even talked about that in Sysml, a block definition diagram. So some of these would be just blocks at a certain point when you're first conceptualizing a design. Items are the inputs and outputs of a system. Components are a subsystem of a system. Interfaces are the connections between the systems and the components. And the VV&A, so the verification, this is the determination that the physical design meets the requirements. Validation is the determination that the right system has been developed. And finally, the acceptance is the determination that the stakeholders accept the system. Here is something called an entity relationships diagram of the key concepts. And so this is a sample entity relationship diagram showing many of the chapter concepts and their relationships. So ultimately, we're developing a system, and you can see that that system has functions, and those functions consist of items. Those items have interfaces, and it just goes on and on in terms of how you can be relating these various things and thinking it in terms of an entity relationships diagram. This starts to give a little bit of insight into, well, maybe there is a possible argument for using discrete math, and we're going to be talking about that in a couple chapters, but I'm just going to skip over this for now, other than that short introduction that I just mentioned. One of the things that Booty uses here and there is an elevator scenario. I'm not going to focus too much on this example, so it's going to be a little bit streamlined. We're going to be focusing more on satellites and CubeSats as a way of giving an illustration of how we can be doing system engineering. But at least let's talk about how a system like this works and get some more insight into the system engineering process. And so for the scenarios, and so a passenger requests a service, that would be an example of a scenario. Passenger enters the elevator car. So this has to be developed in such a way that it's going to be safe for the passenger to enter the car, and the door has to open before he comes in and after he leaves. And then a maintenance person needs to repair an individual elevator car. So there needs to be set up in such a way that it's maintainable. And so how and what are the ways that it's designed such that maintenance can be done in an effective way. As I stated, we're not going to really be focusing on IDEF, the integration definition, and specifically IDEF 0. And so these charts are going to be for reference. It's been around since the 1970s. My perspective, it tends to be a little bit more software centric, and we're trying to be going more towards something that would be a complete system and not geared towards a hardware or software modality. And the IDEF 0 is more more focused on the functional modeling. And so this whole ideology of what we're talking about is process modeling, and in a very detailed way that has been around for quite some time. So IDEF 0 is a method designed to model the decisions, actions, and activities of the organization or systems. You may have some connections with using IDEF 0 in the future. And so maybe that would be something that might be of interest to you. I did find this one reference that was trying to show the relationship between an IDEF 0 and a Sysml diagram. And so this is an activity diagram showing the relationship between those two. So this is really making the Sysml look as much as possible like an IDEF 0 diagram, where it doesn't need to be this constrained in terms of this flow, but you can at least see some comparisons if that is a useful thing for you. And I have the reference for that here if you want to be looking it up. Okay, here is an example of an IDEF 0 block diagram for the elevator system. Like I said, I'm not going to be focusing on this in detail, but if you just look at the general blocks and what goes in and out of each block, you can start to see some general flow of how it tends to work. An elevator, like any system, there's going to be a hierarchy of requirements. And so you start with the objectives, and then you get into performance types of requirements that are talked about, availability as well. And so those are all things that are there. So in terms of the requirements hierarchy, we briefly showed this in an earlier slide. And so we have the input and output requirements. We have the system-wide and technology requirements. We have the trade-off requirements and the qualification requirements. And so if you look at some of the requirements documents, this would be an example of how that could be laid out. And you could have different parts of a document that would be focusing on each one of these. Okay, in our practical guide to Sysml, they use an analogy of a car. And so within a car, there's various subsystems, if you will. You think of the engine, transmission, the body, brakes, suspension, wheels, and the interior. And so this is an example of how you could be breaking that out. And so then if you get more specific, say if you're talking about the engine train and how that goes from the fuel and the control from the accelerator, how that then passes to the drive and actually causing an acceleration force on the wheels, we can then get those more detailed examples. We're going to be focusing more on CubeSats. And so this would be one way of showing this. This is a block definition diagram in Sysml, which is related to a class diagram from its parent, if you will, of how it evolved from UML. And this is showing some of the characteristics from UML. So you can have a mission. And so the things that you're going to need for a CubeSat mission is you're going to need to have a CubeSat. You need to have a ground station that's going to communicate with, and you have this CubeSat doing a mission, and so you need to have some way of capturing the actual mission operations. And so those would be three main blocks under the CubeSat mission, if we think of that from a high-level point of view. So once again, getting into the specifics of the elevator requirements. So this is just a sample. And so we're seeing those different things, the input and output requirements, the functional requirements, the system-wide and technology requirements being laid out here in a certain subsection of that requirements document. And here we're just showing some more examples of the system function. And just think in terms of that provide elevator service. In general, that's what we're trying to do. We can have then the next level when we have more details in the functional decomposition, accepting the passenger, controlling the cars, moving the passengers, and making it serviceable. And so those would be 4 blocks. And so here we're, instead of seeing it with an IDEF0, we're just showing that in a more general way in terms of the physical architecture. So what about a comparison between top-down system engineering and Sysml? And so here we're seeing a mapping from one to another. And there's almost a complete one-for-one mapping with these different types of diagrams, and then the database of information that is contained below that. It doesn't deal with risk and trade studies. It doesn't deal maybe as much, which is maybe something that's debatable with creating the physical architecture, and something that Booty talks about as this morphological boxes. We will touch on that, but won't dwell on that in much detail. But everything else, in terms of a top-down system engineering approach, it's captured by these different diagrams that are within Sysml. In terms of the system engineering tools, there's a lot of them. So I'm not showing all the tools. I'm just doing a comparison. First of all, this is the tool that we will be using for the models that each of the students will be creating, and that's using something called visual paradigms. It's a flexible model-based system engineering tool, and the community edition makes it freely available to do Sysml type of modeling. But there's also a lot of pay-for add-ons that you can be doing a lot more of the type of capability that the enterprise tools that are out there. We're not going to be using the Vitek core. This would be something that would be focusing on the IDEF0 kind of relationships, but just for completeness, if people see that in the textbook or are curious about that, that's the tool that they use. Okay, in terms of the 4 main pillars within Sysml, there's the behavior diagrams, the requirements diagrams, the structural diagrams, and this parametric diagram. And sometimes it's considered just another example of a structure diagram, but so that's the reason why I have it showed in 2 different places. But in general, what you'll see is there's these 4 different blocks, and so that's what Sysml is used. There is a detailed Sysml model and delegati that we'll be leveraging, and we will go through a lot of the details of the practical guide, from the practical guide to Sysml for giving us insight into how Sysml can actually be used. So I'm going to skip over the stuff for core made by tech, but in the textbook it talks about that, and so you can have these available to you. So the first is the system engineering classes, the common system engineering relations. And so that's going to be it for this lecture. Thank you very much.